In section 6.1, we introduced the dot product, which we could use to quickly measure the cosine of the angle between vectors. One of the things we discovered was that if the dot product of two vectors is 0, then either one of the vectors is 0 or they're perpendicular to each other. So when the dot product is 0, we say the two vectors are orthogonal. So in section 6.2, we want to discuss having a set of vectors where each vector is orthogonal to every other vector in the set, so that the dot product of any one vector with any other vector is going to be equal to 0. So we've got an example here of an orthogonal set. So if we take u1 and we dot it with u2, we would get 1 times 1 plus 1 times negative 2 plus 1 times 1, which would be 1 minus 2 plus 1, which is 0. Or if we dot u1 with u3, we would get 1 times 1 plus 1 times 0 plus 1 times negative 1. So we would get 1 plus 0 plus negative 1, which is 0. So u1 is orthogonal to both u2 and u3. And the only other pair to check is u2 and u3. So u2 dot u3 would be 1 times 1 plus negative 2 times 0 plus 1 times negative 1, which would again be 1 plus 0 plus negative 1. So all three of these vectors are orthogonal to each other. And so if we put them in a set, then that set would be an orthogonal set. So, okay. So one thing that we like orthogonal vectors for is that if you have a set of non-zero orthogonal vectors, that set will automatically be independent. So the idea is, the thing for independence is to show that there's no non-trivial linear combination that creates the zero vector. So let's suppose we have a linear combination of u1, u2, and so on. Somewhere in the middle there would be ci, ui, and so on, plus cp, up. And suppose that linear combination creates the zero vector. Then I can show that c1 is 0, and c2 is 0, and c3 is 0, and so on up to cp. The basic trick would be whichever one you want to show is 0. Like let's say I want to show ci as 0. I'm going to dot everything on both sides here by ui. When I do that, I just distribute that dot product to each of these things in the sum. But u1 times ui will be 0, u2 times ui will be 0, and so on, right? The only one that won't be 0 will be this one, ci ui dot ui. And over on the other side we have 0 dot ui would just be the number 0. Okay, this is the only one that's not 0, right? Because a non-zero vector can't be perpendicular to itself. So this would just be equal to the magnitude of ui squared, and since ui is not the zero vector, I know that that's not 0, so I can divide both sides by the magnitude of ui squared and just get that ci is 0. So you could do that p times, right, and show that c1 and c2 and so on up through cp would all be 0. That means that there's no non-trivial linear combination that creates the zero vector, and therefore this set is independent. One reason we like to have orthogonal sets are for orthogonal bases. So if we have a basis for a particular subspace and all the vectors in that basis are orthogonal, it makes it really easy to write other vectors in terms of that basis, because we can compute the weights just by doing a dot product. So that's what theorem 5 says. Suppose we have an orthogonal basis. So we have a set of non-zero vectors, right? And each one is orthogonal to every other one. Then it's really easy to take any vector in the subspace and write it as a linear combination of the vectors in the basis. Because all you have to do to find the coefficients is just take the vector that you want to write and dot it with each individual basis vector and divide by the magnitude of the magnitude squared of that basis vector. So you can see where this is coming from, because if you dot both sides of this linear combination by ui, you would find y dotted with ui is equal to c1 u1 dot ui, but that's going to be 0, and c2 u2 dot ui, that's going to be 0. All the dot products will be 0 except for the one where we dot ui with ui, right? That one would be ci times ui dot ui. So solving here for ci, since the results of dot products are all scalars, everything here is a scalar now. So ci is going to be y dot ui divided by ui dot ui, or that would be y dot u sub I divided by the magnitude squared of u sub I. You can see that if we were to choose this basis, so not only were each vectors, all the vectors orthogonal, so not only orthonormal, but if each vector was actually a unit vector, that would make it really, really easy, right? Because then this number would be 1 for all of those. So we would just calculate these coefficients simply by doing a dot product. So here's an example of how we could do that. We have these three vectors again. They're non-zero and they're orthogonal to each other, so we know that's automatically independent, and so we have three independent vectors in R3. That's the most you can have, right, and have a basis. So we know that that's a basis for R3 because they're orthogonal to each other and therefore independent, and there's three of them, and R3 has dimension 3. So let's say we have some other vector, 1, 2, 3, and we want to decompose it in terms of this basis. So I'm basically saying, okay, how could I write 1, 2, 3 as some scalar times 1, 1, 1 plus some scalar times 1, negative 2, 1 plus some scalar times the third basis vector 1, 0, negative 1. And normally when we do this, we would have to make these the columns of a matrix, and then we'd have to solve that matrix, but it's much easier because our basis is orthogonal. So for example, to find C1, all we have to do is to dot both sides of this equation by U1. So U1 is 1, 1, 1. So I'm going to get C1 times U1 dot U1 plus the other ones. If I take U1 dot U2, that's going to be 0, so I'll have C2 times 0, that's just 0, and C3 times U3 dot U1 will also be 0. So I'm just going to get C 1, 2, 3 dotted with 1, 1, 1 is going to be 6 equals C1 1, 1, 1. We have 1 plus 1 plus 1. We do the dot product, so that's 3. So I can see that C1 has to be 6 divided by 3, or just 2, right? And I can find the others kind of in a similar way. Remember in Theorem 5, it just said C2 is going to be 1, 2, 3 dotted with, that's the vector we want to decompose, dotted with the second basis vector, which is 1, negative 2, 1. And then we'll just have to divide by U2 dot U2, since it's not 1 in this case. So when we do this dot product, we get 1 minus 4 would be negative 3 plus 3 would be 0. Okay, so we have 0 upstairs. So we're going to have 1 plus 4 plus 1 is going to be 6. 0 divided by 6 will be 0. And finally, to get C3, we can just take our vector 1, 2, 3 and dot it with U3, which is 1, 0, negative 1, and divide all that by 1, 0, negative 1, U3 dotted with itself, right? So we get our coefficients here. We have 1 plus 0 minus 3 would be negative 2. And if we dot U3 with U3, we get 1 plus 0 plus 1 is 2. So that tells us that C3 is negative 1. So we can just check that really quick. If we take, so C1 is supposed to be 2, so if we take 2 times U1, and C2 is supposed to be 0, so we're going to take 0 times U2, that's 1, negative 2, 1, and then we're going to take C3 is supposed to be negative 1, so we're going to have negative 1 times 1, 0, negative 1, and see what happens when we combine them. We're going to get 2 plus, so 2 plus 0 minus 1 would be 1, and the second entries are going to be 2 plus 0 plus 0 is going to be 2, and the third entry is going to be 2 plus 0 minus minus 1 would be 2 plus 1, that's going to be 3. So we figured out how to make that linear combination just by doing dot products.